A data-grounded summary of can knowledge be translated by a machine? Hans Gottscha's 2026 article published on August 18, 2026, received October 15, 2025, revised March 31, 2026, and accepted April 12, 2026, challenges the claim that machines can translate scientific and engineering texts to an almost perfect level. Drawing on his experience evaluating funding applications, Gottscha builds a philosophical linguistic case against the hype surrounding AI and large language models. The paper is structured into 5 main sections plus 2 postscripts and uses a wide range of numerical evidence, from speaker populations to citation counts and historical dates, to ground its arguments. 1. The scale of the translation problem, sections 1 to 2. Gottscha opens by noting that the projects he assessed aimed to translate in principle, any language into any other language. He immediately introduces a numerical reality check. There are between 6,000 and 7,000 languages in the world, yet only a few hundred are substantially represented on the Internet. To illustrate the disparity, he cites Irish, which has only 20,000 to 40,000 speakers and is classified by UNESCO as definitely endangered. By contrast, Gujarati, a script he could not even get an AI to accept, has about 60 million speakers. This numerical contrast, 20k, 40k versus 60 million, exposes the absurdity of building universal translation systems for every language while basic script support remains missing. In section 2, Gottscha gives a concrete example of polysemy, Wittgenstein's German word spiel. He queried Microsoft's Bing on August 14, 2025 and received a confident but flawed answer. This leads to a key numerical distinction, 2 possible English counterparts, game versus play, and the realization that machines cannot resolve such philosophical nuances because they lack access to the pragmatic context that human readers use unconsciously. 2 Linguistic hurdles with numbers, section 3. Gottscha defines a text as chains of words with blanks and a word as a string of letters, limiting his discussion to alphabetical scripts. He then provides a detailed syntactic test using a Danish headline from September 13, 2025. The phrase no jet held and det end form anden creates a dual interpretation problem, a the supporters dream about something other than the chairperson, or b they dream about something other than what the chairperson dreams about. He then shows the results from DeepL across 6 languages, Swedish, Lagerkamp and Ordførende Posten Party Chair, Interpretation A. Dutch, Achterban and Voorzitter, Interpretation B. German, Hinterland and Voorzitsend, Interpretation A due to dative case. Italian, dual ambiguity like Danish. French, Entourage and Precedente, correctly resolves as B. Finnish, Tukijakaot and Pohinjataja, interpretation alike Swedish. This 6-language comparison demonstrates that even a relatively simple sentence produces inconsistent resolutions across machine translations, because each target language's grammar and the absence of a shared pragmatic context force different, often incorrect choices. Gottscha then examines the Danish reflexive pronoun sin in the phrase siden drab et pas sin mand since the murder of her husband. He notes that Danish grammar requires sin to refer back to the subject, which, in that sentence, is hustru wife, thus logically implying the wife murdered her own husband. This is an anaphoric pronoun dilemma for which no single Danish word can simultaneously encode reflexivity and gender. He then lists DeepL's output in 5 languages: English, German, Swedish, French, Italian, plus Finnish, showing that none of them replicate the Danish logical trap. The numerical count, 5 to 6 target languages per test, reinforces that each language has its own irreducible grammatical quirks, making any universal translation model inherently fragile. 3. Scientific translation and the 3 obstacles, section 4. In Section 4, Gottschalk introduces a tripartite classification of facts: universal, particular, singular, and then, in subsection 4.1, explicitly lists three phases: obstacles for translating a research paper, I the source language, 2 the mechanism human or electronic, and 3 the target language. He also cites the Stanford Encyclopedia of Philosophy, noting that a search on September 22, 2025 returned 1,921 entries with the word knowledge or affiliated terms, a stark numerical testament to the philosophical complexity of defining knowledge. In subsection 4.2, Gottschalk tests DeepL on 3 real scientific papers, David L. Scher 1995, From English to German. C. S. Unnikrishnan 2025, From English to German and French. Akshang Mishra 2025, From English to French and Swedish. He reports that, surprisingly, the outputs are in general, well-formed and accurate. However, this does not vindicate AI, rather, it proves that scientific writing is intentionally unambiguous, so the statistical patterns are easy for software to mimic. He then contrasts human brain processing with machine processing. The human brain works introspectively and updates its mental universe only when predictions fail, whereas AI continuously trawls the internet. He cites Otsuka 2023, p. 126 to explain the mathematical form of a deep neural net as y equals gx, w, a single equation that reduces translation to a regression problem, devoid of any semantic understanding. For historical and energy-based arguments. Section 5. Gottschalk brings in historical numerical references to show how scientific knowledge has repeatedly been overestimated. He quotes Albert A. Michelson in 1894 claiming all fundamental laws were discovered, and Simon Newcomb in 1888 declaring astronomy nearly complete, both statements made more than a century ago, yet utterly disproven by subsequent discoveries like quantum mechanics. This serves as a warning against contemporary techno-optimism. He also gives a striking physical comparison. The human brain's neural signals travel at a maximum of 120 ms 432 km/h, while computer electronics operate at the speed of light, yet machines still cannot match human cognitive efficiency, despite consuming vastly more energy. This numerical contrast underscores his argument that raw speed and scale do not equate to genuine understanding. 5 conclusions with 5 numerical statements. In Section 5, Gottschalk condenses his position into a numbered list of 5 statements. He is not opposed to AI or LLMs. He does not aim to undermine ordinary users' reliance on AI. Software is a useful practical tool with the energy consumption caveat. He is skeptical of comparing machines to human brains. The similarities are not there. He worries about the disruption if influential groups blindly trust AI answers. He also notes that, when he asked Bing on September 23 at 16:52 what are humans and why are we here, the AI answered the what but ignored the why, a failure that illustrates the limits of statistical pattern matching. Finally, in Postscript 5.2, he cites Bernard Bozami's 2023 paper, which quotes the director of Siemens Digital Experience Center as saying he knew nothing about mathematics, a remark that elicited Bozami's warning that no one knows at present what the real limits of the technologies at our disposal are. This caps the paper's numerical and historical evidence, leaving the reader with a clear conclusion: machines can assist, but they cannot translate knowledge, because knowledge resides in human minds, not in low-voltage currents or statistical regressions.